This is the second video for 1D kinematics. Picking up from where we left off, we were talking about distance and displacement, as well as vector quantities. We're going to continue with vector and scalar quantities, but now progress adding time into our calculations, and we're going to be doing speed and velocity. In the English language, they're kind of synonymous with each other, and they'll be used without thought between the two, but for physics, there is a definitive difference. Speed is with distance. It's a scalar quantity, can be positive only. Velocity is used with displacement, can be positive or negative because it's a vector quantity. Both can be determined graphically. If you look at the equations on the middle of the screen, there's distance over time, but delta d over delta t, and velocity is the delta x over delta t. So if you're calculating slope, that's the rise over run, it's delta y divided by delta x. You'll be able to have a distance versus time graph, and the slope of the graph will be speed. You could have a position or displacement versus time graph, and that'll give you velocity. So here's where the algebra skills are going to kick in. Besides just solving the equations, you're going to have to be able to do graphs as well. Every now and then you're going to see something pop up as instantaneous velocity. In fact, almost every single one of our calculations after this first week or so will be instantaneous velocities and instantaneous speeds. To do that, you'd have to take a limit, and therefore you can see the equation with the limit there where time is approaching the zero instantaneous moment. If you're looking at that equation and you have no idea how to even work that, the good news is you don't have to. If your job is to find the instantaneous velocity, then we're going to be using either a different equation than the one that you see there, or you're going to be doing it on a graph. So take a moment. If you're watching this for the first time, you need to start getting word connections. Meaning, anytime you see the word instantaneous, you have to immediately connect it to the word tangent. An instantaneous velocity is going to be a tangent line on a graph. Instantaneous acceleration, when we get to that in a little bit, that's a tangent line. So anytime you see instantaneous, think graph, think tangent line. First practice problem. How long will it take the sound from the starting gun to reach the ears of the sprinters if they're stationed at the beginning 100 meters away from where the person was firing the gun? We are going to make the assumption that the speed of sound is traveling at approximately 340 meters per second. Because they're saying speed of sound, then I'm going to probably use the speed equation. Sometimes you'll see it with a V, sometimes you'll see it with an S. Both are okay as long as you do distance divided by time. The two variables that you know are the speed and the distance. So I'm going to substitute those in. I don't have to show the algebra. I can just immediately use my calculator or use my head and rearrange the equation, which you have to be able to do flawlessly, and then write the time, which is the answer. We'll get into sig figs, but again, for the most part, as long as you don't do more than 3 significant figures, where in this case it's 2, just the 2 and the 9 are significant, then you're fine. Because there's only 2 sig figs here in the 340, although arguably both of these are 3 because it's exactly a 100 meter race and this is an exact speed. So theoretically there are 3 sig figs. When you solve problems, you're going to have to show all of your work, as you can see here. So what I mean by that is almost every single physics problem that you'll have in this class is going to be graded on quizzes and tests on a 3-point scale. It helps for the first time till you get used to the variables and used to the equations that you write down all the given information. But your 3 points are for writing all the appropriate equations. The second point is for showing all the correct substitution into those values. And then the third point is for the correct answer with units and sig figs. So I'll go back a slide. By writing this equation on the paper, I immediately got 1 point out of 3. I've already earned 33.3% of the points for this problem by taking the numbers from the problem and substituting them in to their appropriate variables. I still haven't even done any math, haven't even reached for the calculator. I have now scored 66.7% of the possible points by having the correct answer with the correct number of sig figs and the correct unit. I scored the third point and I just got 100. So even if you have math problems, you can still get 2 out of 3 points per problem. That's very helpful for students that make simple mistakes versus multiple choice, which is all or none. So we started at the beginning, but we'll reinforce it again. Velocity is not the same thing as speed in physics. Velocity is going to be a vector. It uses displacement. You can have positives and you can have negatives. Speed is going to be scalar, meaning it's only going to be positive, and you're going to use distance. But they will always have the same unit, which is a meter per second. So you have to convert everything in this class to meters and convert everything into seconds. So if you measure something in the lab in centimeters, you need to convert it to meters. Go and try another practice problem. You are a particle located at the origin on the number line, on the x-axis, and you're going to determine the time it takes to move from the 0 mark to the 10-meter mark and then back to the 0 mark with an average speed of 0.5 meters per second. So because they said speed, I know I'm going to use the speed equation. Speed is distance over time. Again, I can use v, it's fine, because I'm still using a d and not an x or delta x. The total distance would be 20 meters because you're going there and back, 10 meters out, 10 meters back. Plug in 20 for my distance, plug in my speed of 0.5, solve for my time, and you get 40 seconds. If you're going to do half a meter every single second, then it's going to take you 2 seconds to go 1 meter, hence it'll take you 40 seconds to do the whole 20. For part B, what's the particle's average velocity? Well, the velocity equation is the change in x over the change in time, but the change in x is 0, so therefore the velocity is 0. Your final position is the same as your initial position. 0 meter minus 0 meters is 0. Even though time occurred, your displacement is 0. Therefore, your average velocity is 0. For the next one, a ball is kicked along the ground 12 meters away, and then it is passed back, but only 4 meters towards its origin. If this entire action of going out 12 and back 4 is done in 2.5 seconds, answer the following. What's the total distance traveled by the ball? Well, that would be 12 meters out plus the 4 meters back, so the total distance would be 16 meters. For part B, we're doing average speed. Speed is distance divided by time. So there's my equation, distance divided by time, with the d for distance and speed. Substitute in my values, 16 meters divided by 2.5 seconds. So the average speed is going to be approximately 6.4 meters per second. 2 sig figs with my 16 meters from before, so I'm keeping the same 2 sig figs here. For part C, we're going to do average velocity. This line that goes above, if I didn't mention in the first video, that's the symbol for average or constant. So the average velocity is the change in displacement or the change in time. The initial position was at 0. The final position is at the 8-meter mark. Because you're going to go out 12 in a positive direction, then you're going to turn around and come back 4 meters in a negative direction. So you're only going to be 8 meters away, minus your initial position, divide that by your time, which is still the same total time. You're going to get half the amount, 3.2 meters per second. If you're starting to understand speed and velocity, then we're going to add something to it. It's the whole point of this course. We're going to keep adding one thing to it, and then one more thing. We're going to add acceleration. Acceleration is defined as the change in speed or the change in velocity of an object over time. Similar to the previous equations, we can also do slope If I gave you a v velocity, vt graph, velocity on the y-axis and t on the x-axis, then the slope of that graph would be your acceleration. Anytime you have to find the instantaneous acceleration, it'll be done on a graph where you're going to draw, hopefully you already made the mental connection, a tangent line. It is a vector, so it can be positive or negative. As mentioned in the previous video, there are no negative numbers. There's no negative integers in physics. You only have positive integers, but you can have a negative referring to the direction. That's your reference frame. The average acceleration is just a line above it. In English language, when we say decelerate, we typically mean you're slowing down. But there is no such thing as deceleration in the physics world. You either have a positive acceleration or a negative acceleration. And this will be confusing in the beginning, but hopefully when we show you here in a second another slide, a very simple concept is extremely important. So here is what we were talking about. If your velocity vector and your acceleration vector are pointing in the same direction, then the object will be getting faster. As you can see here, the car is moving to the right, trying to get to the donut. It's got a positive velocity going to the right, a positive acceleration going to the right. They are the same signs you are going to speed up. Same thing with the one below it. Your velocity is going to the left. Got to get that donut. The negative acceleration, that means your acceleration is negative, meaning left. Even though it's a negative acceleration, you're not slowing down because they're pointing in the same direction. They're working with each other. So you're moving in a direction that you're also accelerating in that same direction. You're going to get faster and faster and faster just in a leftward motion. If they are opposing signs, opposing directions, then you are slowing down. You're moving to the right, but you're slamming the brakes, so therefore your acceleration is in the opposite direction, then you're going to slow down. And same thing down here. Moving to the left, but you have a positive acceleration, you're slowing down. This very simple concept is missed by a lot of first-time physics students. It is an extremely important concept for the rest of the year. This is a skill, some knowledge that you want to just learn. So take the time now to understand this. The next practice problem is a horse is running with an initial velocity of 11 meters per second. It begins to accelerate at negative 1.81. So immediately apply what you had just learned on the previous slide. It's a positive velocity, but a negative acceleration. They are opposite signs. That means it's going to be slowing down. Plus, when you read the next sentence, how long does it take the horse to stop? Right there, it's telling you it's coming to rest. It's slowing down. So you can make the mental connections even before the English comes into the problem with the second sentence. I am going to use the only acceleration equation that has been given to me so far. It's the change in velocity or the change in time. The change in velocity can be rewritten outward if I wanted to. So I can cross multiply the time over, and then I can change the change in velocity so I get this equation. Now sometimes you'll see me write it in the college format versus the high school format, but if there is no symbol, that means final. This is a O or 0, it means not, so that's V naught. That means initial. You can think of it like an O for original. So you will see it also written in this format, a linear format versus a fraction format. I can plug in the values. Final speed will be 0. The initial speed will be 11. The acceleration would be negative 1.81, solving for time. I could also just plug it in here. On the numerator, it would be 0 minus 11. Over here would be the negative 1.81, and I'd still be solving for my time. I don't have to show the math. I can just show the answer, and then 11 is 2 digits, 1.81 is 3 digits. I'm keeping my least number of sig figs, which is 2. 1 point for writing the equation, 1 point for showing the substitution, 1 point for the correct answer, sig figs unit. 3 points. There are 3 equations known as the kinematics equations. So first kinematics, second kinematics, and third kinematics. These all have names. The name of this equation is the average acceleration. Average because there's a line above it. This one starts with displacement, x position. So this is your position or displacement with constant acceleration. This one starts with velocity. So this is called the velocity with constant acceleration equation. As noted by your 3 A's with lines above them, you can only use these if your acceleration is constant. And for the first almost half of the year, they're always going to be constant. Get familiar with your equations, get familiar with your variables. X or Y or Z are displacements. Subscripts just tell you what you're talking about. So that's my position in the end. That's my displacement initially. Initial velocity, final velocity. Lots of problems will be using these the whole year, and you'll have to quickly adapt to the fact that not all problems are going to be done with one equation. As we progress, there are going to be 2, 3, 4, sometimes 5 equations to solve one problem. And eventually, when we get to the third unit, you're going to create your own equations. So here's our first practice problem after seeing those. An object is moving on the ground for a total displacement of 15 meters. If it comes to a complete stop during the trip, what's the initial speed if it had a constant acceleration of -2 meters per second per second? That's meters per second squared, the unit for acceleration. It's got displacement, so I checked it off. There's my delta x. That's what that represents. It's asking me for the initial speed, that's v0 or vi, and I know the acceleration. So I'm looking for a kinematics equation that was on the previous slide that has x, a, and v, but it doesn't have time. So here's this equation. That was one of the ones. However, I don't know the time. So that means I don't know the initial velocity. That's my answer, and I don't know time, which means there's 2 variables in the equation. I can't solve it. That means I have to do another equation. Algebra 101, you can only solve an equation that has 1 variable. If you have 2 variables, then you need 2 equations. You have to do a system of equations, which we do get to very soon. So we'll try the next one on the list, technically the third one on the list, but the next one down that we're choosing. I know all of these variables except for the one that I'm looking for, which is the initial velocity. So this one is correct. That's the one I want to use. So I write this equation down to give myself 1 point. Then I substitute in all the numbers. It's coming to a stop. Final velocity 0. Initial velocity is my answer. 2 is just part of the equation. My acceleration is -2. My change of x was 15. I solve without having to show the math. This is going to be roughly 7.746 and then extra numbers. Looking at the original problem, that's only 1 digit. So I need my answer to be 1 sig fig, 8 meters per second. The next one. An object is traveling with a constant speed for 20 meters for 5 seconds, then accelerates itself and increases its velocity 3-fold, 3 times faster in 4 seconds. So 2 parts, A and B. How fast was it initially traveling? Which means 2 things are occurring. There's a constant speed, and I'm going to call this part 1, and then something else happens. Because during part 1, there's no acceleration. You're moving at a constant speed. During the second segment, there's an acceleration. So I cannot combine them. There's one equation and only one equation to use when there isn't an acceleration. And then there are multiple different ones that we can choose from for when there is an acceleration. Constant speed means constant velocity, your acceleration is 0. There's only one equation to use for that. That's the average velocity, or constant velocity equation. The change in x or the change in time. I know the change of x is 20. I know the change in time is 5. That means the constant speed for that first 5 seconds is 4. Now for part B, there's an acceleration, which means I have to use one of the three kinematics equations that have acceleration in them. The only problem is the answer for part B is asking me how far. That means I first have to figure out what the acceleration is. Otherwise, I would always have two variables. I know that the initial speed is 4. I know the final speed is going to be 3-fold faster, so that's 12. I'm solving for A. My time is 4 seconds. My acceleration during part 2 is 2 meters per second, or 2 meters per second squared. I needed to do this work first, so I can now find the answer to part B. So for part B, I'm going to use one of the kinematics equations. The second one, it's displacement with acceleration. The initial position, I'm just going to say is 0. The initial speed is 4. Time was 4 seconds. The acceleration was 2. 1/2 is part of the equation, 4 seconds squared. Now I made my initial position 0 because it's only asking me how far did I travel during the 4 seconds. If it asked how far did I travel during the whole 9 seconds, then my initial value would be 20 because I already covered 20 within the first 5 seconds. But this equation is only accounting for the 4 seconds where we were accelerating. Simplify the problem down, I get 32 meters. That'll be the cutoff for the second video. The third video will pick up from here.